looking at our next lab, we're going to implement a larger finite state machine. In Lab 6, we had some small finite state machines, but we have a lot more knowledge now, and we want to go ahead and make a larger finite state machine controller. Taking a look at our finite state machine that we're going to use, we see that we now have 6 states, and we have 5 inputs and 2 outputs. And so this is much larger than our small finite state machines that we did in Lab 6. But the process of designing the controller is exactly the same. Using our Quartus 2, we know that the first thing that we want to do is to create a project called Doorlock. And so we can do that. We're going to follow exactly the same procedures that we did in the last lab. And then we're going to create a BDF called Doorlock FSM. And so when we go to Quartus 2, we can go ahead and bring that up, and we see that we have a project called Doorlock, and we have a BDF called Doorlock FSM. Taking a look at what we want to do with this, let me enlarge the screen. And so the first thing that we need to do is to basically determine our combinational logic equations. We know that when we look at our finite state machine that we have 6 states, and so we're going to go ahead and make up a table. Now it is your choice as to how you want to implement this. If you choose to use one-hot encoding, then you don't need to make the table. But if you're going to use binary encoding as you did with Lab 6, then you need to go ahead and make a table. And so let's just first start by making our table and understanding how we want this to work. We know with 6 states, we need to figure out how many flip-flops we need for our state register. And so with 6 states logged to the base 2 of 6, and rounding up using the ceiling function, we know that we need 3 flip-flops. And so I have gone ahead and listed all of the state assignments for all 6 states if you're going to encode in binary. And then also I began to create your state table, and so you have the beginning of the state table here with the wait state and the start state, and so you can go ahead and finish that before you actually start encoding. Now I really recommend that you do this on a sheet of paper. It's fine with me if you type it in. You can see that these are all comments, and I will not be grading that. We're not grading you on your comments, but you need to be able to debug your code. And so I really recommend that you use a sheet of paper and do your engineering design work on paper rather than trying to write it into this .v file. Okay, and so we have basically, once we've written our next state table, we can encode, and so we can list all of the possible values. And so taking a look back at Quartus 2, we have our, cancel that. We have our Doorlock BDF, Doorlock FSM BDF, and we see here that we have our combinational logic. We've made it into a symbol after our .v files. And so we have all of our inputs. We have our next states coming out of here into our state register. As we said, we're going to need 3 flip-flops, and so with our state register, we have our 3 flip-flops. This was given to you on the website under the manual, and so we have that here, basically the same image telling you that you're going to need 3 flip-flops if you're encoding in binary, okay? And so then back to our Quartus 2, we have our state register. We create a symbol out of this BDF, and then we can use that on a higher level. We see here that we have our state registers that we've used. We have our combinational logic. Okay, we've also added an extra piece of circuitry here. We said that we want to add this circuitry here. Basically what this does is it creates that A input. We talked about before that when the user presses the button, we want to only see it for 1 clock cycle. And so we had the finite state machine In class, we talked about it, how we would generate that A, but here we have the circuit for it. So make sure that you include that into your FSM, your Doorlock FSM.pdf. And so here we have it. Okay. Once you have this level of design done, you can go ahead and you can run your tests. We know that looking at our FSM tests, we have our test. It's looking for Doorlock FSM, and the module that's going to instantiate is the Doorlock FSM. And so that is indeed, this is the one that's being tested. Okay, so once you've tested that, you can run ModelSim, and hopefully you'll get all tests passed, and you'll see something like this with your screen. Just again, expanding this out. We have a lot of data here. We have a lot of tests going on, testing all of the cases, or many of the cases that you might encounter. And again, with a very large finite state machine, and this is actually very small, but you can see we have lots and lots of test cases that are occurring here in this particular test bench. Okay? And so make sure you run ModelSim on the Doorlock FSM. That would be your top level when you ran the simulation. Okay, and after you've done that, you can go ahead and make certain that your QSF is the QSF that has all of the pin assignments. Make sure that you have the pin assignments, and that your names match the names. Create a symbol out of this BDF, right? And then open up a new BDF, and then you have your FSM that you created from the lower level. Notice here that I have my pin assignments. I put in some button debouncers for each of my inputs, and then I have my outputs here. And so they're all attached to the wires that are associated with my Doorlock .qsf, and from there you should be fine. So you can go ahead and implement your circuit.